I'm Joseph Dauben, and the music you hear in the background is typical music of the Renaissance, music that would have been familiar to the famous Italian scientist Galileo Galilei, or to his father, who was himself a musician. The significance of this music for Galileo's important studies of motion, and especially his experiments with inclined planes and his analysis of accelerated motion associated with the celebrated Leaning Tower of Pisa, will become clear a bit later in this program, devoted to the genius of Galileo and the relation between his role in the scientific revolution and the equally remarkable achievements of Renaissance artists, reflected in part in the discovery and application of mathematical perspective. But first, what of Galileo and the scientific revolution? Among the great figures of the Western scientific revolution of the 16th and 17th centuries, Copernicus, Kepler, Galileo, Descartes, Newton, and Leibniz all had at least one thing in common. They were all mathematicians. And yet of these six figures, two stand out as being conspicuously different. For only Galileo and Newton were systematic experimenters, and of these two, it was Galileo, at the beginning of the scientific revolution, early in the 17th century, who demonstrated the extraordinary effectiveness of experimental observation of nature, coupled with the analytical power of mathematics. It is also interesting to note that while the revolution in mathematical astronomy, which is a technical theoretical science, had its origins in Northern Europe, in Poland with Copernicus and Prague with Kepler, the experimental side of the scientific revolution had its origins in Italy. This is equally true for the life sciences, where the great advances of anatomy and physiology are associated with the likes of Andreas Vesalius, Fabricius of Aquapendente, Realdus Columbus, and even William Harvey, all of whom worked in Italy and even more specifically at Padua in the 16th and 17th centuries. One question that immediately arises about the origins of modern science is the role that mathematics played, specifically in the hands of Galileo, along with another question that this program will also examine. Why was it in Italy that the experimental sciences emerged for the first time in both the physical and the natural sciences? To answer these questions, we will also have to consider the general context in which Italian Renaissance science arose, and how the mathematics of Galileo's new science, as he called it, was related to the great works of Italian Renaissance painters and architects. Moreover, by considering the interconnections between art and science in the Renaissance, it is possible to trace the origins of Galileo's own, particularly Renaissance approach to nature. As we shall see, the values and attitudes he held were those shared by Italian humanists generally. But first, before it's possible to make sense of these connections, it's necessary to say something, if only briefly, about Galileo himself. Galileo Galilei was born near Pisa in 1564, the same year in which Shakespeare was born and the same year in which Michelangelo and Calvin died. After studying at the University of Pisa, he was appointed to the chair of mathematics, but as this picture of Pisa reminds us, it was there, of course, that the famous Leaning Tower might well have suggested Galileo's most famous experiment. This computer simulation, showing the tower, illustrates what Galileo's demonstration would have shown. First of all, the theory which virtually everyone accepted at the time was the traditional theory of Aristotle, who believed that heavier objects fall more quickly than lighter ones. Consider, for example, two objects, one twice as heavy as the other. Imagine Aristotle at the top of the Leaning Tower of Pisa dropping off two cannonballs, one twice as heavy as the other. According to Aristotle, it should fall twice as fast. If it were 4 times heavier, it should fall 4 times faster. But in fact, what the Leaning Tower of Pisa type of experiment demonstrates, when actually performed, is that Aristotle was wrong. That no matter what the difference in weight, two heavy objects will fall simultaneously at virtually the same speed. Recently, it has been fashionable to question whether or not Galileo ever dropped anything off the campanile, or Leaning Tower, of the Duomo in Pisa. If he did so, it certainly could not have been an experiment in the modern sense of the word. Can you imagine running up and down the Leaning Tower of Pisa, trying to drop objects of different weight simultaneously from the edge of the tower at the very same time, which is not easy to do, and then observe how quickly they fall, especially when the time elapsed would only have been a matter of seconds, and nothing like the stopwatch or any other convenient timing device had yet been invented. Actually, whether or not Galileo ever performed his famous experiment on the Leaning Tower hardly seems to matter. A similar experiment demonstration had already been published by Benedetti Giambattista in 1553, and the test had also been made and published by the Flemish engineer Simon Steven in 1586. As for Galileo's interest in disproving Aristotle's theory about falling objects, years later he said that he had first thought about this during a hailstorm, when he noticed that both large and small hailstones hit the ground at the same time. If Aristotle were right, this could only happen if the larger stones dropped from a higher point in the clouds, but at virtually the same time, or that the lighter ones started falling earlier than the heavier ones, neither of which seemed very probable to Galileo. Instead, the simplest explanation was simply that heavy or light, all hailstones fell simultaneously with the same speed. In any case, Galileo's interest soon turned from falling bodies to astronomy. Only a few years earlier, a remarkable and controversial discovery had been made by the Danish astronomer Tycho Brahe, who found a new star in the constellation Cassiopeia in 1572. Actually, it was a supernova, one that disappeared 2 years later. But this was enough to challenge directly another tenet of Aristotle's, namely that the heavens were perfect, immutable, unchanging. When another nova appeared in 1604, Galileo was persuaded to give 3 public lectures in Padua, where he was then teaching. These aroused considerable interest, so much in fact that no hall was big enough to accommodate everyone who wanted to hear him. Like Tycho Brahe, Galileo used the nova as a pretext to challenge the Aristotelian idea that the heavens were unchangeable, immutable, perfect. 5 years later, rumors of an invention made by a Dutch spectacle maker reached Venice, and these led Galileo to construct his first telescope in July of 1609. It wasn't long before Galileo began to make a series of startling observations, including the discovery of innumerable stars never seen before, mountains on the moon, and the 4 satellites of Jupiter, the movements of which he carefully plotted from day to day. He was soon ready to publish these discoveries in a book, the Sidereus Nuncius, or Starry Messenger, which caused an overnight sensation. Galileo named the moons of Jupiter the Medicean planets, in honor of his former student Cosimo and the famous Medici family, thanks to which he was shortly thereafter appointed chief mathematician and philosopher to the Grand Duke of Tuscany in Florence. All of these discoveries, and others, posed yet more direct challenges to Aristotle's idea of the perfection of the heavens. Some Aristotelian astronomers refused to look through Galileo's telescope. Others tried to deny what he had seen. The Roman Catholic Church, however, was becoming increasingly concerned, and a young Dominican, Tommaso Caccini, was the first to denounce Galileo officially and the Copernican theory his observations seemed to support from the pulpit during a sermon in the Duomo or Cathedral of Florence. A few years later, as concerns mounted, Galileo was officially advised by Cardinal Bellarmino on the Pope's behalf to proceed cautiously and speak only hypothetically about the Copernican theory, but not as if it were actually real. Galileo returned to Florence and continued work in his book, but now he gave more emphasis to mathematical arguments rather than physical arguments, as the Pope wished. But when the book finally appeared in 1632, it raised an immediate storm of protest, leading to Galileo's arrest and famous trial by the Inquisition in Rome, which found him guilty of having published an heretical book. In the end, Galileo had no choice but to repent and confess that he had gone too far in his book. He was sentenced to life imprisonment, which he spent for the most part in his own villa at Arcetri near Florence under the surveillance of the Inquisition. Even so, Galileo in his last years now undertook his last and perhaps greatest work, his Discourses on the Two New Sciences, which has been described as the cornerstone of modern physics. It was smuggled out of Italy to France and published in Leiden in 1638. In this book, Galileo presented the true laws of accelerated motion and falling bodies, as well as the fundamental theory of projectile motion and important applications of mathematics to a host of physical problems. When Galileo died in 1642, totally blind and almost 78 years old, Pope Urban VIII refused to forget his feud with Galileo and refused to permit his burial with a suitable monument. Instead, Galileo was buried unceremoniously in the Church of Santa Croce in Florence, and only 100 years later were his remains moved to their present magnificent tomb opposite that of Michelangelo near the entrance to the church. By now it's possible to appreciate several basic and fundamental aspects of Galileo's scientific genius. Above all, his early work seems to have concentrated upon arguments against Aristotle, arguments involving a sustained pattern of observation and demonstration requiring little in the way of mathematics and concentrating instead on physical experience. His most revolutionary observational discoveries came with the telescope, and these provided, for the first time around 1610, a number of good physical arguments in favor of the Copernican theory. Later, however, Galileo had two additional concerns: the problem of defending that theory against attacks from the Church without recourse to physical examples, as the Pope had insisted, but primarily with mathematical arguments. Secondly, his impressive discovery of the parabolic nature of projectile motion, elaborated fully in 1638, seemed in a very profound way to display the essentially mathematical character of physical phenomena. As we shall see in a more careful examination of the mathematical arguments Galileo developed for accelerated motions, especially the parabolic trajectories of projectile motions, through a number of computer simulations, is that Galileo believed that nature was inherently mathematical, that mathematics was the language of nature, and that mathematics was the key to understanding the reality behind the appearance of natural phenomena, for example, accelerated and parabolic motions. What Galileo achieved in revolutionizing physics was to show how observation, careful measurement, and attention to the structure of a given event all led to an appreciation of the hidden causes that ultimately expressed the pervasive mathematical unity of all nature. But Galileo was not the first to have done this, although in terms of astronomy and physics he was clearly a pioneer. But Renaissance artists, painters, sculptors, and architects had been observing nature with a special interest in depicting it faithfully, realistically, from the early 15th century on. In fact, by turning to the problem of art and science in the Renaissance, it is possible to find what I believe are important roots for Galileo's own peculiarly realistic and idealistic approach to nature. For the values and attitudes Galileo held were ones he shared with Italian humanists, including philosophers, artisans, even musicians. The question now is to determine what those values were, the important ones for Galileo's science, and to decide what role they played in Galileo's experimental and mathematical revolution. In the same year that Galileo's Dialogue Concerning the Two Chief World Systems was published in 1632, Rembrandt painted his famous anatomical lecture, graphically representing what physicians had learned from Renaissance artists, that nature was accurately representable only by virtue of careful observation, through anatomical dissection revealing the hidden structure underlying the human form. Artists of the Middle Ages, lacking a theory of mathematical perspective and more interested in depicting religious, spiritual truths rather than the real physical world, did not worry about whether the objects on this table in an early 15th century version of the Garden of Paradise would fall off or not. Even as Italians like Giotto began to show a greater sense of real space and form, lacking a theory of perspective made this view of Arezzo look rather peculiar, certainly not a realistic view that soon, with a mathematical theory of perspective, artists could easily achieve. In fact, the first steps towards a new sense of artistic reality were taken early in the 15th century. One of the earliest masters of the human form was Masaccio. In his Expulsion from Paradise, painted about 1427 in Florence, you can easily see the results of careful observation of human anatomy. Masaccio's atom reflects an underlying structure of skeletal frame and superimposed muscle, as does his fresco of Peter baptizing the neophytes. A century later, art and anatomy combined dramatically in the work of Andreas Vesalius, the Flemish physician whose major work on the structure of the human body was illustrated by one of Titian's students. The illustrations provide a graphic, detailed record of the musculature and skeletal framework of the human body, and literally seem to pare away, layer upon layer of skin and muscle, to reveal the hidden structure underneath. The first artist to perform actual dissections to improve his anatomical knowledge may well have been Antonio Pollaiuolo. His painting of the Martyrdom of St. Sebastian, his last work completed in 1475, is a tribute to his virtuosity. The forced, unnatural positions of the archers in particular seem all too cleverly planned, so that Pollaiuolo could demonstrate his skill at depicting anatomical reality. In much the same way, but even more dramatically, Luca Signorelli undertook to complete a series of frescoes in Orvieto between 1499 and 1504. In both The Damned Consigned to Hell and in The Resurrection of the Dead, Signorelli seems to have adopted contrived positions for many of his figures, again to show his skill in representing the human figure. The ultimate achievement of this sort, however, was brought to perfection by Michelangelo, whose mighty atom in the Sistine Chapel seems a direct evolution, artistically, from Signorelli's in Orvieto. In fact, we know that artists of the late 15th century like Michelangelo and Leonardo actively pursued anatomical dissections to perfect their understanding of the human form, as in this drawing by Michelangelo and in this anatomical study by Leonardo, an excellent example of his fascination, both scientific and artistic, with all aspects of nature. What Renaissance artists had clearly achieved through careful observation of nature, including studies of anatomical dissections, was a means to recreate the three-dimensional physical reality of the human form on two-dimensional surfaces. In part, the key to this achievement lay in understanding the underlying hidden structure of the human body, which then enabled the artist to produce realistic representations of what he saw on the flat surface of a wall in the case of frescoes, or on a wooden panel or paper in the case of paintings or drawings. If artists in the 15th century had learned to portray with faithful accuracy the human form through careful observation and anatomical dissection, a similar inspiration occurred to those seeking a corresponding dramatic reality in the representation of physical space. By means of a mathematical theory of perspective, a means was devised early in the 15th century for translating the reality of three-dimensional natural phenomena onto two-dimensional surfaces, producing visually realistic copies. A correspondence was thus made possible through mathematics between the representational reality of the artist and the physical reality of nature. The first to undertake a series of optical experiments of this kind was the Florentine artist Filippo Brunelleschi. His most stunning accomplishment, in fact, is the stupendous dome which crowns the cathedral in Florence, a work which occupied him intermittently from 1417 to 1434. The technical difficulties involved in erecting the new dome underscore an important aspect of his talents. He was a daring innovator with a solid knowledge of mathematics and mechanics. Perfectly in keeping with Brunelleschi's interests are experiments he is reported to have performed on the subject of mathematical perspective. Antonio Manetti, Brunelleschi's biographer, writing a century later, describes one of these experiments in which Brunelleschi painted an exact copy of the baptistry in front of the famous cathedral in Florence, which you now see behind me, on the surface of a small mirror. To demonstrate that this was indeed an exact replica that would fool the eye, Brunelleschi drilled a small hole in the panel and then stood directly in front of the baptistry, looking through the peephole to see the real building behind. He then held up a mirror in front of the panel, which blocked the view of the real building, but now reflected the painted version of the same scene. By moving the mirror in and out of the way, Brunelleschi could show that he had indeed produced an exact copy of the three-dimensional octagonal building on the two-dimensional surface of his mirror. But now, working with the two-dimensional version, it was possible to analyze its structure mathematically. As Brunelleschi found, there was a mathematical key, not only a central vanishing point which you can now see generated by the computer, a vanishing point that was defined exactly opposite to Brunelleschi's own position, standing in front of the baptistry, but this point also determined the horizontal line which the computer now draws, the horizontal line of the horizon itself. The horizon line not only passes through the central vanishing point, but is also the line on which the two-point perspective, defined by the oblique vanishing points, also falls, namely the lines defining the perspective of the baptistry itself, as the computer again graphically demonstrates. What is clear from Manetti's description is that the panel constructed by Brunelleschi was made by careful mathematical calculation. And in Brunelleschi's case, it seems reasonable that he devised the method of perspective for architectural purposes. He is said by Manetti to have made a ground plan for the Church of Santo Spirito, on the basis of which he produced a perspective drawing to show his clients how it would look after it was built. And here, fading back to the original perspective drawing and then to the actual church again, it is clear to see how successful the new art of mathematical perspective was in depicting spatial reality. But this was just the beginning. 10 years later, Masaccio applied the new method of mathematical perspective even more spectacularly in this fresco of the Holy Trinity, where the barrel-vaulted ceiling is incredible in its complex mathematical use of perspective. Here, lines following Masaccio's actual geometric framework are overlaid to make clear the structure of the perspective itself. From the geometry, it was actually possible to work backwards to reconstruct the full volume and measured accuracy of the three-dimensional space Masaccio depicts. And this illustrates exactly the sort of flexibility Brunelleschi had in mind in being able to translate schemata directly between two- and three-dimensional spaces. While we do not know how far Brunelleschi intellectualized his system mathematically, it was not long before a decisive step was taken by Leon Battista Alberti, who published a treatise on perspective, De la Pittura, in 1435. Once Alberti's treatise was published, knowledge of perspective no longer had to be passed on by word of mouth. For some, it became a matter of consuming artistic, even philosophical interest. Among the best examples is Uccello's fresco of the Deluge in Florence, completed about 1448. Here, linear perspective is used to present an elaborate architectural setting. The real object of fascination, however, is Uccello's rendering of the mazzocchi, the curious checkered hats, of which there are two in the Deluge. Uccello had actually drawn such wonderful polyhedral forms in studies of perspective drawings, and these clearly demonstrate the mastery he had of the new mathematical techniques. The culmination of the mathematical theory of perspective, combined with a philosophical program of the most intense and religious order, comes with the work of Piero della Francesca. His St. Anthony's Polyptych in Perugia shows how masterfully he was able to use the new theory of perspective. The colonnade of the Annunciation is a mathematical and artistic tour de force, and is reminiscent of the architectural trompe-l'oeil of an actual perspective colonnade in the Palazzo Spada, fashioned by Galileo's contemporary Borromini in Rome. Here you can see the long colonnaded portico with a monumental sculpture in the distance. But this is actually an illusion, a trick of the eye played with the help of mathematical perspective, and the trick is revealed as these two figures of equal height show the perspective at work. Mathematics was equally important to Renaissance artists in determining the correct proportions of the figures they drew. Leonardo da Vinci followed such principles explicitly, measuring not only the proper proportions of the human head, but the dimensions of the various parts of the anatomy of the horse as well. This was all embodied literally in the most complete visual statement of the harmony between mathematics and nature in his famous drawing of the human figure, proportioned in keeping with the architectural perfection of the square and circle. What does all this have to do with Galileo and the advances he made in the art of physics, the mechanics of motion, in support of the Copernican universe, and the new science of the early 1600s? It's no coincidence, I think, that the artistic Renaissance and the scientific Renaissance should have both developed at first largely in Italy. Scientists like Galileo were doing exactly what Renaissance artists had been doing all along, with growing skill and increasingly sophisticated techniques in their depictions of nature in realistic terms since the late 15th century. The veracity of their mathematical vision was well established by the time Galileo began thinking about the mathematics, the geometry of space nearly a century later. What Renaissance artists had discovered was that in addition to careful observation and attention to underlying physical structure, and often this meant anatomical structure, mathematics was an especially useful tool for translating the physical reality of three-dimensional objects in three-dimensional space to realistic illusions of that same reality on only two-dimensional flat surfaces. Galileo, like Renaissance artists of the 15th century, was interested in form, in the underlying reality of the natural world. He too was interested in the sort of physical reality that he felt his mathematics and his telescope were making clear for the first time. Light, optics, mathematics, all were as important keys for Galileo as they had been for Brunelleschi, Alberti, and Piero della Francesca. But there is no greater, more impressive example of all this than Raphael's magnificent School of Athens. Here Plato on the left holds a copy of his Timaeus and gestures upward to the ethereal realm of his eternal forms. In contrast, Aristotle's hand is outstretched. He holds a copy of his Nicomachean Ethics and indicates with his gesture the worldliness, the concreteness of his contributions to philosophy. On the right are the geometers and astronomers. Just off from center, wearing the clothes of a 16th century stonecutter, is Michelangelo. Throughout the School of Athens, there is an emphasis on mathematics, number, ratio, harmony. Pythagoras is represented by his theory of mathematical harmony on the left, Euclid by the perfection of geometry on the right, and the elaborate perspective design of the architectural setting seems to embody both. It's now time to ask how this emphasis upon mathematics, number, ratio, indeed a mathematical theory of structure in space, is related to Galileo's impressive studies of motion and his similarly architectonic view of space, one that also emphasized the importance of mathematics, number, and ratio, especially in Galileo's analysis of accelerated and projectile motion. Behind me is a replica of Galileo's workroom, as recreated at the Deutsches Museum in Munich, Germany. As you can see, it contains many of the mathematical instruments and experimental equipment Galileo used in his studies, the most prominent of which is the inclined plane. This was carefully constructed to help with his study of motion, accelerated motion in particular. Earlier, we discussed the kind of demonstration Galileo may well have performed himself from the Leaning Tower of Pisa, which disproved Aristotle's theory of motion by showing that objects of different weight fall with the same accelerating speed, hitting the ground at virtually the same time. Galileo wanted to study gravity and how it affected acceleration in greater detail, but falling objects accelerated too quickly, and the time was too short to make accurate observations. Was there any way he could try to slow down the effect of gravity, to observe the rate of acceleration in slow motion? This is exactly what the inclined plane allowed Galileo to do. At an angle of 60 degrees, the rate of descent along an inclined plane is not much slower than the case of a freely falling object. But at 30 degrees, you can see that it is now possible to begin measuring ratios of time and distance with reasonable accuracy. The force of gravity continues to act on the billiard ball as it begins at time t0 to roll down the plane. and it goes faster and faster until at the bottom it rolls onto the horizontal plane. At this point, as Galileo reasoned, gravity is no longer pulling on the ball to continue accelerating its motion. Instead, the effect of gravity is now uniform or constant, and ideally, the billiard ball will now continue to move in a straight line with a constant uniform motion. This, in fact, was one of Galileo's important insights about motion and is a version of the law of inertia. If we now lower the plane even more, the force of gravity will be diluted even further, so that, for example, if we now roll the billiard ball down the inclined plane from rest at t0, the intervals of time and distance can be measured even more accurately. But how? Galileo had no stopwatch, not even a pendulum clock. Actually, he used a clepsydra, a version of the ancient water clock which provided a relative measure of time in terms of amounts of water collected in a jar as the billiard ball rolled down the inclined plane. But there was another way to measure time intervals that Galileo also used. Equal intervals of time are easily measured by musical intervals. This brings us back to the Renaissance music we heard at the beginning of this program, for it is not difficult to measure equal intervals of time quite accurately by ear, and Galileo found something quite surprising when he tried this. Let's begin with the plane at an inclination of 20 degrees. Start the ball rolling and count equal intervals of time as it rolls down the plane. Now look at what happens if we take the distance covered in the first time interval as a unit of measure. In the first second, the ball is covered a distance of 1 unit. In the next second, it covers 3 times this distance, and in the next second, because acceleration continues to make the ball move faster, it covers a distance 5 times the initial distance. As Galileo discovered, from 1 second to the next, as the ball rolls down the inclined plane, the ratios of the distances covered increase by odd numbers, by intervals of 1, 3, 5, 7, 9, and so on. Trying this again with the plane at different angles always produces the same progression of distances covered in equal time intervals. This is always in proportion to the sequence of odd numbers, 1, 3, 5, and so on. This progression of distances by odd numbers, as Galileo observed for uniformly accelerating objects, is quite remarkable. But there's more. Let's now analyze this a bit more carefully. After 1 second, the ball has covered a distance of 1 unit. In the next second, it covers 3 more units. So at the end of the first 2 seconds, it has covered a total of 4 distance units. In the third second, it covers 5 more units, for a total distance after 3 seconds of 9 units. And if the ball continues for another second, it will cover 7 more units for a total distance of 16 units after 4 seconds. As Galileo realized, after considerable effort, both experimental and mathematical, there is an even more remarkable connection here between time and distance, namely that acceleration acting uniformly on a falling object does so mathematically in such a way that the distance covered is directly proportional to the square of the time. And we can write this as d is proportional to t squared. Galileo brought his lifetime of insight as an experimenter and mathematician to a conclusion in his greatest work, published in 1638, the Dialogues on the Two New Sciences. Here, in the second half of the book, he took up the question of projectile motion. This illustration reflects the general opinion before Galileo, which followed largely Aristotelian lines, but incorporated as well a later theory of impetus, which maintained that an object shot from a cannon, for example, followed a straight line until it lost its impetus, at which point it fell abruptly to the ground. Later, simply by more careful observation, as this illustration from a work by Niccolo Tartaglia clearly shows, it was realized that projectiles actually follow some sort of a curved path. But what sort of curve? No one knew until Galileo. It was another essential insight that led Galileo finally to his most remarkable conclusion about projectile motion. First of all, he reasoned that a projectile shot from a cannon is not influenced by only one motion, but by 2. The motion that acts vertically is the force of gravity, and this pulls the projectile down by the times squared law. But while gravity is pulling the object down, the projectile is also moving forward horizontally at the same time. And this horizontal motion is uniform and constant, according to his principle of inertia. But could he demonstrate this? In fact, by using his inclined plane again, Galileo was indeed able to demonstrate that a projectile is subject to two independent motions, and these combine to provide a precise sort of mathematical curve. Observe what happens when we let the billiard ball roll down the inclined plane, increasing its speed due to the accelerating force of gravity, until it reaches the bottom of the inclined plane and then continues to roll along the horizontal plane in a straight line with a uniform speed. What would happen if, instead of rolling along the horizontal plane, the ball were now allowed to simply fall freely once it got to the bottom of the plane? If Galileo were correct about the horizontal and vertical motions being independent, it would still continue to move horizontally with a uniform constant speed, but gravity would now begin to pull it down vertically at the same time, the distance increasing proportionally to the square of the time elapsed. And this is exactly what Galileo found. Here you see the experiment simulated with the computer. Notice how the path of the ball now traces an exact curve. Here, in fact, is a page from one of Galileo's manuscripts in which he writes down the figures he obtained in performing this experiment himself. What he actually came to see is that, in fact, the curve has an exact mathematical shape. It is one the Greeks had already studied and called the parabola. The extraordinary conclusion Galileo reached in his book on the two new sciences is that the path any projectile follows is a parabola. And he drew exact consequences from this discovery, which, as he said, could only have been achieved by the sort of exacting analysis that mathematics made possible. This now brings us back to the ideals embedded in the iconography we discussed earlier of Raphael's impressive fresco, The School of Athens. For in his way, Galileo might be said to have synthesized the fundamental principles and insights about nature that Plato and Aristotle had first begun to explore in antiquity. From Plato, Galileo took his faith in the ultimate rationality of nature and the fact that the key to understanding nature was to be found in the ideal, perfect world of mathematics. But from Aristotle, Galileo also understood that to understand nature, one must also be a systematic observer, and that it is only through experience and careful study of nature that the hidden secrets, the mathematical structures underlying the appearance of physical events and phenomena, can be discovered. Galileo achieved a synthesis of observation and theory in a way that was strikingly modern, and yet was also a product of the centuries of Italian humanism and the tremendous burst of energy we associate with the artistic renaissance we discussed earlier in this program. New discoveries advanced the arts as well as the sciences, and many of these were due to new instruments and methods, especially ones related to mathematics. This was exactly the mix of ideas embedded in the iconography of an atlas by Marco Coronelli, which indicates that the exploration of the world depends upon observation using scientific instruments, as well as upon mathematics, which those instruments represent. In contrast to the limits set on man's search for knowledge by the traditional expression ne plus ultra, no further, Coronelli proclaims the spirit of the new age of science, by writing plus ultra, yet further, on the banner of the trumpeting angel. This was also the point of the frontispiece to Francis Bacon's great work, the Instauratio Magna, published in 1620. This work contained Bacon's fundamental treatise, the Novum Organum, a new method for scientific investigation to replace the old and faulty one of Aristotle. The book was given an imposing subtitle, True Directions Concerning the Interpretation of Nature. The ship, prominently displayed on the book's title page, is sailing through the Pillars of Hercules. Tradition had always placed these as the limits of man's possible exploration. But instead of the traditional ne plus ultra, Bacon's title page in fact declares, as did Coronelli's, plus ultra. The Latin quotation at the foot of the waves, taken from the book of Daniel, reads, "Many will pass through, and knowledge will be increased." Renaissance artists had contributed greatly to that knowledge by the time Galileo was doing his first work at Pisa. The humanist artists of the Italian Renaissance had performed their own dissections to promote the study of anatomy. They had invented mathematical perspective to make possible the accurate, realistic portrayal of physical space. The literary humanists had managed to revive all sorts of classics, in particular the works of Plato. Christopher Columbus had directly challenged the limits to the finite European world of Ptolemy's geography. In short, the bounds of human knowledge were expanding at a rapid rate. Thus it comes as no surprise that Italian artists of Galileo's day responded favorably, even enthusiastically, to the new discoveries that science itself was making. It was Galileo's friend, Ludovico Cigoli, who incorporated the latest discoveries of his telescope hot off the press in Galileo's Siderius Nuncius in 1610 in his own version of the Assumption of the Virgin, painted just 2 years later in 1612. In Cigoli's painting, notice the treatment of the moon at the Virgin's feet, rendered as though it were seen through the telescope, exactly as Galileo had recorded it in his own pen and ink drawings only a few years earlier. In closing, how can we draw all of the diverse strands of Renaissance artistic realism, especially Brunelleschi's discovery of perspective, with Galileo's experiments on acceleration and his analysis of projectile motion? It's clear that Renaissance artists were seeing a new world, thanks in part to mathematics and the new perspective, literally, that mathematics provided. Galileo not only inherited this perspective, but a philosophical sense as well that had been inspired by Renaissance philosophers, especially Neoplatonists, namely that the underlying reality of the world we perceive is essentially mathematical. This was exactly the point made in Riccioli's dramatic depiction of the hand of God, creating the world according to mathematical principles, number and weight and measure, written clearly on his fingers to make no mistake about the inherent, essential, mathematical character of the physical world. Renaissance artists and architects had already succeeded in translating physical space into the mathematical terms of proportion and perspective to produce works that tricked the eye and rivaled nature. Galileo used mathematics with equal skill to reveal the underlying structure of physical space and motion to show that these two could be reduced to mathematical analysis. In connecting physical space and real motion, which could be observed experimentally, with the ideal and uniform change of his Neoplatonic mathematical world, Galileo also served to bridge the early stages of the scientific revolution in Europe and figures like Copernicus and Kepler, with the later unifying achievements of Descartes, Newton, and Leibniz. Thus, in a very direct way, it was mathematics that not only facilitated the art of Renaissance perspective, but provided the key as well to Galileo's new science of nature. In both cases, the essence of physical reality was understood in terms that could be reduced to basic mathematical principles.